Now let's take a look at the areas of the brain that are involved in sending and controlling and regulating these muscle signals that go through the spinal cord out to the muscles and leading to our movement. So you'll see that there's a bunch of areas here that are involved. And some of these are really important. Well, they're all important, but some of them are kind of high-level decision-making areas. Others are going to smooth out muscles, help us not, trip and fall, help us maintain some level of coordination and balance and so on. So there's different roles that are being played here. One of the decision makers in movement is the prefrontal cortex. This part of the brain, in keeping with what the prefrontal cortex does in general, remember, decision making, goal-oriented behavior, it's going to select the appropriate behavior and its target. So what's the objective of what you're trying to do? Using a combination of bodily and external information. So it's a highly connected area of the brain that knows about the position of your body, the position and location of other people and other objects, and so on. And it's going to, depending on what's going on in your environment, help you choose the appropriate plan of action, especially when there's more than one option. The premotor cortex, the clue here is the word pre. It combines information needed for movement programming, such as the target that's being reached for and its location, which arm to use, and the arm's location. So really simply, if you're trying to open a door, the target is going to be the doorknob. And it's going to need to know the location, which arm to use, and the arm's location. This area is typically active before we move. And there's a section in your book that talks about how recordings in the premotor cortex show activity right before activity in other movement areas, in particular the primary motor cortex, which is the one that's actually sending the signals out to your muscles. So we're going to skip supplementary right now. The primary motor cortex sends information out to the muscles. It executes voluntary movements by organizing the activity of unspecialized cells. It adds force and direction control. It tends to not just activate a particular muscle, but it will activate a group of muscles that are all needed to reach your arm out, grip the doorknob, and turn it. So it's going to allow a coordination of all the muscles that are involved in doing that. The supplementary motor area assembles sequences of movements. So you might want to associate sequences, the S in sequences, with the S in supplementary. Also, I kind of think about it as a dancing area because we need this area to be able to dance properly. So it assembles sequences of movements such as eating or playing the piano. It coordinates movements between the two sides of the body, task sharing between the hands, for example. So it's really critical for those sequences of movements so that we can alternate left and right, for example. And also piano playing is a good example. How we wouldn't just press one piano key and then another, but there's a whole string of coordinated keys that get played. So think of the supplementary motor areas as stringing together the sequences of movements, allowing us to coordinate both sides of the body. The basal ganglia is not in the cortex, neither is the cerebellum, of course. So we're leaving the cortex now. All these areas above are in the cortex. The basal ganglia is deep in the brain. It's not a cortical structure. So it's going to work a little more in the background, but we're going to see it's really important. It uses information from secondary areas and the somatosensory cortex. In other words, association cortex areas that bring together numerous sensory information, as well as the somatosensory cortex that's bringing information about our bodies. And it integrates it to allow for smooth movements. And it does seem to be involved in learning movement sequences. So when you're first learning movement sequences, whether because you're learning a new dance or how to drive or how to play an instrument, it's very involved. But then once they're learned, it's kind of done with that part of it. The cerebellum maintains balance, refines your movements, controls your eye movements to compensate. So for example, if you move your head to the right, or if you spin your body to the right, but you need to keep your eye on a person walking to your left, it will automatically move those eyes to compensate. So if you're looking at your screen right now, just move your head left and right and keep your eye on the screen. You'll be using your cerebellum. The cerebellum is definitely involved in directing your eye movements to compensate for the movement of your head. It's also involved in the learning of motor skills and becomes less important as the skill becomes, familiar to us. So here we can see how all of these areas are super involved in providing information to each other. So let's take a look at here, the primary motor cortex. A lot of arrows are coming in here, right? So the motor cortex is getting information from the somatosensory cortex about what your body's doing. It's also getting information from the prefrontal cortex regarding what the prefrontal cortex just decided, hey, this is what we're going to do. We're going to go out the back door instead of the front door, for example. And it's also getting information from the premotor cortex, which has planned out these movements and tried to integrate, the different muscles that you're going to use. And in addition, it's using visual and auditory information through these other pathways. So it's very well connected. We can see here also the supplementary motor area. Yeah, in case you are doing a series of movements, that's going to send information first to the motor cortex. And then the motor cortex determines which muscles have to be activated and sends that information down to the spinal cord where they can eventually innervate your muscles. And we also see the cerebellum here as well being involved. The primary motor cortex, just like the somatosensory cortex, has what's called a homunculus. It's a mini version of your body laid out. Different areas of the motor cortex control different parts of your body. Here we're seeing that the size of the body part lets us know how much of the motor cortex is involved in making that part of the body move. So here's a hand area. Wow, right? A lot of our motor cortex is dedicated to moving a relatively small part of our body, our hand. But if you think of like the fine motor movements that your hands can do, it needs more processing power, more neurons to help it do that. In contrast, few of us can do really sophisticated fine motor things with our elbows. And so the elbow, even though it's really maybe just a little bit smaller than the hand, is taking up a much smaller section of the motor cortex, right? Same thing with like, our lower back or our calves. So the calf is larger than the hand and yet is not needing nearly as much motor cortex to help it process that fine motor movement that the hand does. And look also at the face. Yep, the face is really important. We make a lot of movements to create facial expressions, and in particular the lips, the mouth, and the vocal tract, and all of that require a huge level of fine motor control, and so they get a lot of territory here in the motor cortex. So the amount of motor cortex is proportional to the needs of that area for moving muscles in a very precise way.
A classical illusion that has been published in 1998 by two Americans, Botvinnik and Cohen, two American neuroscientists, is the rubber hand illusion. The rubber hand illusion consists in placing, let's say, one's left arm out of sight, out of vision, and placing in front of the eyes of the subject a hand in plastic, a rubber hand. And then the experimenter will stroke, let's say, the index finger of my left hand, and at the same time the left index finger of the rubber hand. And if he does this synchronously for a minute, up to 2 minutes, certain subjects, 2/3 of all subjects, will start experiencing this hand for some moments as if it were belonging to their body. So this is one way, and this is normally investigated by questionnaires. So the subject will be asked a certain number of questions to respond to. And then there is a second measure, which is, in my opinion, even more interesting, because if you then, after these 2 minutes of stroking, will close the eyes of the subject and ask them, well, now point to where your hand would really be, they do not point with eyes closed to the real arm, they will point towards the rubber arm.
I really felt that my hand was transposed and into that false hand that was presented in front of me. The feeling was really an awkward feeling, a very strange feeling of having a false hand belonging to me. We visually see that the hand is false, but we can't separate that from the fact that we actually feel our hand in that place.
By simultaneously stimulating fake rubber hand and the real hand, something that is felt and something that is seen on a hand is integrated. Under normal conditions, when I see something close to a hand and I feel touched at the same position, this is always on my hand, at least I guess in 99% of all cases. So by disintegrating these two types of information, the experimental psychologist interferes with those brain mechanisms that we have through phylogeny, but also through our own development, learned that our brain has learned to fuse together.
Isn't that super interesting? And it's the motor cortex that's active during the illusion, and it connects the touch from the real hand with the visual information of the rubber hand, allowing the illusion to occur, allowing the person to really, really flinch and sense that it's their real hand that's going to be poked during the process.